Assalamu alaikum. I am Muhammad Jahangir Alam, lecturer in physics. I welcome you all in my online class. First of all, thanks to Almighty that He has given me the ability to take this class. Dear student, I also hope all of you are well by the mercy of Almighty and carrying on your regular studies, staying at home. Right? Dear students, today we are going to discuss an important topic from our physics second paper and from chapter 4, that is the magnetic effect of current. Our today's topic is Biot-Savart law or Laplace law and its application. Scientists Weierstedt first discovered that a current carrying conductor can create a magnetic field around the current carrying wire. You know it. So to verify or to determine the magnetic intensity or the magnetic field created by the current carrying conductor, scientist Laplace gave an theory or law, and later on scientist Biot and Savart in 1820 experimentally verified the law. So according to Biot-Savart law, if AB is a current carrying conductor and if we consider a small length dl and the intensity of the magnetic field due to the current carrying conductor at point P, which is at r distance, is depend on the points or on the factor. It's directly proportional to the magnetic field of the magnitude of the magnetic field depends on the directly proportional to the current. Here the current through the conductor is I. So if the magnetic field intensity at point P is denoted by dB, dB is directly proportional to the current I, right? Then they said that directly proportional to the length of the conductor. If the considerable length of the conductor is dl, then dB is directly proportional to dl. Then they said that directly proportional to the sine of the angle between the line connecting the point and the midpoint of the conductor and the conductor itself. Here, if the connecting line makes an angle theta with the conductor conductor, then dB is directly proportional to sine theta. Okay, and finally they said that inversely proportional to the square of the distance of the point from the midpoint of the conductor. If the distance of the point from the midpoint of the conductor is denoted by r, then dB can be written as dB is directly proportional to 1 by r square, right? So combining this four expression, we can write that dB is directly proportional to I into dl sine theta divided by r square. Here we can replace the proportional sign introducing a constant. So dB is equal to k into I dl sine theta divided by r square. This constant of proportionality depends on the unit of the measurement of these quantities and the medium. For the air medium, and if the quantities are measured in SI unit, then the constant can be replaced as dB is equal to 4 mu naught divided by 4 pi into I dl sine theta divided by r square. Here mu naught is the permeability of vacuum medium and the value of mu naught is equal to 4 pi into 10 to the power minus 7 Tesla meter per final ampere. Form of the Biot-Savart law is dB is equal to mu naught by 4 pi into I dl sine theta by r square. If the medium is not air, then we can write the expression as dB is equal to mu divided by 4 pi into I dl sine theta divided by r square. Okay, I hope you got it. We are going to see an application of Biot-Savart law, and One of the first application is determination of magnetic field at a point due to a long straight wire carrying current. In our previous we have discussed that the magnetic field intensity at a point at r distance due to a small length dr. Due to a small length dr, the expression become mu naught divided by 4 pi into I dl sin theta by r square. Dear student, you know this magnetic field is due to a small wire, small length dl, but we have to determine here a long straight wire. We have to determine the magnetic field due to a long straight wire. So here we have to integrate this expression to get the total magnetic field due to the total wire. You know the magnetic field intensity at a point P due to the dl length is dB is equal to mu naught 4 pi into I dl sin theta divided by r square. This is for the length of dl, but we have to determine the whole wire. So we have to integrate here. Therefore, to get the total magnetic field B, we have to integrate this expression mu naught 4 pi into I dl sin theta divided by r square. You know here mu naught 4 pi and I are the constant quantity. So we write the expression mu naught 4 pi I into dl sin theta divided by r square. In the expression, dear student, you can realize that dl, l is a variable, theta is variable and r is variable. There are three variable quantities. For the simplicity, we have to convert the value, that is l, theta and r, into a single variable quantity, and that will help us to simplify the expression. Okay, we need to use the limit of the length of the wire, that is from minus infinity to plus infinity, since you are going to determine the magnetic field intensity for the total wire. So here the lower limit is L is equal to minus infinity and upper limit is L is equal to plus infinity. Okay, so minus infinity to plus infinity. Now in right angle triangle OPQ, OPQ is a right angle triangle. Here R is the perpendicular, OQ is the base and R is a hypotenuse. So we can write cosec theta is equal to R divided by A. Therefore R is equal to A cosec theta, right? R is equal to A cosec theta. Again from the same triangle, that is in triangle OPQ, we can write that cot theta is equal to L divided by A. But here we use a minus sign for the special purpose, because in the expression we have to use length is a variable quantity. If Q is the midpoint, then in the negative side L2 will be negative and in the positive L will be positive, right? So from the expression we can write that the L is equal to minus A cot theta, and after the differentiation we can write dl is equal to A cosec square theta d theta, right? So this is the expression for dl. So now we are going to use the value of r and dl in this expression. If this is expression number 1, then we are going to use these two value r and dl in the expression. Okay. So using the value of this expression in the expression, we can write mu naught I divided by 4 pi into dl can be replaced by a cosec square theta d theta into sin theta, right? And r is a cosec theta, a cosec theta whole square. Here we have to change the limit also, because in the previous calculation our variable was theta, but here in the expression the variable was dl, okay, and here the variable is theta. So when the length is minus infinity, you can consider that when the length is minus infinity, in that case theta will be 0 degree, right? And when the L is plus infinity, then the theta will be pi radian or 180 degree. So in that case the limit will be changed to 0 to pi, right? And after the calculation we can write mu naught I 4 pi integration of 0 to pi sin theta d theta by a, right? Dear student, now we can write b is equal to mu naught I 4 pi a into 0 to pi sin theta d theta. So you know the integration of sin theta is minus cos theta. So mu naught I 4 pi a, after the calculation you will get minus cos theta d theta, and the limits are 0 to pi. When if we take out the minus sign in front, minus mu naught I 4 pi a cos theta pi 0, and the calculation mu naught I 4 pi a, you can write cos pi minus cos 0, right? And from the expression we can write b is equal to minus mu naught I divided by 4 pi a into, you know, cos pi is equal to minus 1, so here minus 1, and cos 0 degree is equal to 1, again minus 1. So after the calculation you will get the b is equal to mu naught I divided by 2 pi a, right? Dear student, this is the final expression for the magnetic intensity at a point P due to a long straight wire carrying current, right? I hope you got it. Now we can see the direction of B produced due to the flow of current carrying conductor. We can describe it by the Fleming's right hand rule. Dear student, you know, if the thumb indicates the direction of current, then the toes of this finger indicate the direction of the magnetic field. If I describe with the figure, dear student, if the wire carrying current and the direction of current in upward direction, if we consider the direction of the current in upward direction, then the direction of the magnetic field will be around the current carrying conductor. That is, the current carrying around the current carrying conductor, the direction of the magnetic field will like this. Okay, I hope you realized it. Here we can see an animation to realize the direction of the magnetic field due to a current carrying conductor. I hope it will help you to understand it.
Ørsted's experiment. In 1820, Hans Christian Ørsted performed a simple experiment and discovered the magnetic effect of electric current. The experimental setup, similar to the Ørsted's experiment, which led to the discovery of magnetic effect of electric current, is shown in the animation. A conductor or conducting wire AB lying in north-south direction is connected to a battery V through a commutator or tapping key K and rheostat RH. A magnetic compass needle NS is placed just below the conductor AB. Initially, when no current passes through the wire AB, the magnetic compass needle shows no deflection. When an electric current passes through the wire placed above the compass needle, the magnetic compass needle got deflected from its normal position, which is along north-south direction. On reversing the direction of electric current through the wire, he observed that the magnetic compass needle got deflected in the opposite direction. Also, the deflection of the compass needle increased when the magnitude of electric current through the wire was increased.
Right, dear student, our next application of Biot-Savart law is to determination of the magnetic field at the center of a circular coil carrying current. If we consider this is a circular coil carrying current whose radius is r and center is p, then the current passing through the wire is I, then the magnetic field intensity at point P due to the length dl, according to Biot-Savart law, we can write dB is equal to mu naught divided by 4 pi into I dl sine theta divided by r square. So, in this special case here, the theta between the radius and dl is 90 degree. So, in that case dB is equal to mu naught I 4 pi r square into dl sine 90 degree. Sine 90 degree means 1, right? So, to get the magnetic intensity at the center of the circle due to the total length of the wire, we have to integrate this expression, and in that case if the total magnetic field is B, then B can be expressed as mu naught I divided by 4 pi r square integration of dl. Here the limit of this integration will be 0 to 2 pi because the length of the total wire is 2 pi. So, 0 to 2 pi r. That is shown, you know, the integration of dl will be 4 pi r square l, and the limit will be 0 to 2 pi r. So, using the value you can write 2 pi r minus 0, and after the final calculation you will get B is equal to mu naught I divided by 2 r. This is the final expression for the magnetic intensity at the center of a circular coil carrying current. This is expression for a single loop, but if the number of turns in the coil is n, then the expression will become for n turns. The expression becomes B is equal to mu naught Ni divided by 2r. Okay. So, these are the expression for the magnetic intensity at the center of a circular current carrying coil. This will be helpful for us to solve mathematical problem and creative question. I hope you got it. Right, dear student, now we can consider the direction of the magnetic field due to the current. If this ring indicate the current carrying coil, and here the direction of current I is like this, that is anti-clockwise. If the direction of the current is anti-clockwise, then the direction of the magnetic field will like this. Okay, and when the current in the circular coil is clockwise, then the direction of the magnetic field will like this. Okay, so I think you student got this. One of our practical application of Biot-Savart law is solenoid. You know what solenoid is. If a current carrying conductor wounded over a insulating cylinder, then when current pass through the current carrying conductor, it acts like a bar magnet. That is, two distinct poles it created in the two opposite ends of the cylinder or solenoid. So you can realize it that suppose these are the red marker, the current carrying wire wounded over a cylinder, insulated cylinder, then some magnetic field is created like this, and it act like a bar magnet. Here the north pole is created here and south pole is created here. Dear student, you can realize, suppose this is a current carrying cylinder or current carrying wire is wounded over the cylinder. If you consider like this, you have to hold like this towards you and consider if the flow of current or direction of current is anti-clockwise. If the direction of current is anti-clockwise, then this pole will act like north pole and this pole will act like south pole. But if the direction of the current is like clockwise, then this pole will act like south pole and this pole will act like north pole. You can realize it by keeping in mind a interesting thing, that suppose direction, if the direction of current is like this, here arrow sign indicate the direction of the current. If the direction of current like this, then it indicates N, that is north pole will created at this end. But the direction of current is like this, here the arrow sign indicate the direction of the current, it's act like S, that is it will create south pole at that point, right? I hope
Your channel Physics and Animation. Here in this video we will talk about solenoid and its properties. So let's start. What is solenoid? A long tightly wound helical coil of insulated metallic wire is called solenoid. If you pass an electric current through the wire, a magnetic field is created as shown in the animation. The pattern of the magnetic field is similar to that of a bar magnet. The magnetic lines are almost parallel inside the solenoid and is directed from south pole to north pole. But how to find the north pole and south pole of a solenoid? At a circular end of the solenoid, if the current flows in the anti-clockwise direction, then that end is north pole. It can be remembered with the help of the symbol of anti-clockwise direction, which resembles letter N of capital alphabets. On the other hand, at a circular end of the solenoid, if the current flows in the clockwise direction, then that end is south pole. It can be remembered with the help of the symbol of clockwise direction, which resembles letter S of capital alphabets.
I hope you got it, dear student. Good wishes for you. Thank you very much being with me in my class. But if you have any confusion, you can ask us, you can ask your subject teacher. We will try our best to understand it. So thank you, dear student. May Allah bless all of you. আসসালামু আলাইকুম।